This morning we have a particularly exciting privilege of hearing from Nick McKeown on protocol independent forwarding. This is a notion that's been around for a while, but it's had quite a few different names. So maybe it's settled on one that will last for a while. But you'll also hear from Nick
10 minutes.
How what we are trying to do with this is a little bit different from what you might have thought we were doing or talking about when we first started discussing it a year or two ago. So it's a very interesting development. I'm really thrilled that Nick has taken the interest to dig deeply into this and lead the gang of 12 to make it real. And I hope that many of you will be involved as we go forward. It'll be kind of a next stage in a different dimension for SDN. And the good thing about it is that it doesn't obviate any of the stuff that we are currently doing. And that's important for everything we'll be telling you this week, is that what you're doing now is all really important work. And we're simply going to build on it. So it's my privilege to introduce Nick McKeown, the professor at Stanford University, member of the ONF Board of Directors, and the godfather of SDN.
Thank you, Dan. What I'm going to talk about today is about plumbing. I tend to think of what we do here as we're acting as plumbers, trying to figure out how we plumb the packets through our networks. You don't want to think about that analogy too far, because anyway, particularly on the egress. But the key thing here is to introduce this notion of protocol-independent forwarding. I think many of you have seen papers, ideas, white papers, all sorts of stuff floating around about this notion already. So there's nothing particularly new or novel. I think the thing that's different now is there's a group of people who have come together to try and figure out a common way to do this. And as I'll say later, yesterday the ONF board agreed to start an open source project within ONF that's targeted on this activity. So I should stress, an open source project, not a working group, and I'll talk more about that a little bit later. So I want to thank some of the people. There have been many who have been involved in this effort. We had a group of us who got together in a kind of an ad hoc way over the last few months, from Huawei and Brocade and VMware and Barefoot, to sort of think through what would be a good way to bring this to ONF. We wanted to make it very clear that this is not something to replace OpenFlow. This is not to replace the way that you would use a more fixed function ASIC. This is merely a method for programming devices that lend themselves to be programmed, CPUs, NPUs, and more programmable ASICs. There's also a separate effort that was going on in parallel, in fact several efforts that are going on in parallel, one on this language P4 that some of you may have seen. P4 is a sort of higher level language for describing how you want packets to be processed. And this was an effort, really started as an academic effort about a year and a half or 2 years ago, where the people were listed here. But I do want to give a special shout out to Navindra, who many of you will know. When we started ONF, and we were originally creating the OF 1.0 and 1.1 working groups, Navindra had come and said, hey, you should really think about how to program devices in a common, uniform way. You'll need compilers, languages, a variety of different targets. And it came from work that he'd been doing at Google and other places. And at the time, I think we, ONF, were just not quite ready to be thinking about that, because we wanted to focus on something a little bit simpler to start with. But I do want to acknowledge his pioneering work in that regard. Because really, OpenFlow is a balancing act. You know, the good thing about it is it provides a vendor-agnostic abstraction, a forwarding abstraction, a very simple forwarding abstraction. But it's always had to walk this fine line, this balancing act between two things. On the one hand, it provides this general match action abstraction. We're all very familiar with that. The term match action will probably be said 1,000 times over the next 2 days. It's sort of ingrained now in our heads, and it's hard to now unthink and forget that term, because it's now how I imagine we all think of how packets are processed. And that led to this, you can think of it in the OpenFlow 1.0 as this TCAM model, this very simple TCAM model. On the other hand, it had to work with relatively fixed function ASICs because that's how equipment is built, or at least the higher performance equipment is built and seems likely to continue to be built. And so it was necessary to incorporate the fields that were present in those fixed function ASICs. And hence the 12 fields, that number of fields has grown over time. But the important thing is that this balance was necessary because of the huge investments that take place in ASICs, the long development cycles, we all know those, we're very familiar with those. And so it was necessary to have quite static or slow-moving guidelines so that somebody who's making a large investment knows that the ground isn't going to change underneath their feet after they've done that. And the second thing is that fixed function ASICs are just blazingly fast. I've been tracking this for about 20 years. There seems to be a sort of a rule of thumb that at least the ratio between ASICs, NPUs, and CPUs in terms of processing packets always seems to be about 100 to 10 to 1. We can argue about the details, but it was very important to keep these fixed function devices in mind. So what we've learned along the way is that the importance of multiple stages of match action. That was the first big change that took place. We learned we shouldn't change the spec too fast. It needs to be extensible so that OpenFlow can be used in many different types of network, extensible for different protocols, extensible for different underlying networks, whether they're wireless, optical, or regular wireline, and allow room for vendors to differentiate so that different switch vendors can have different features. And this led to the development of the TTPs. And I think the TTPs have been a fabulous addition to OpenFlow because it was necessary for devices that have a particular behavior to be able to express that to the system in which they operate. And so I think this has been a good development. So nothing I'm saying here is to replace or as an alternative, it's to sit alongside this as a complementary effort. So the way I like to think of the TTP is like this. So here's a sort of very comic picture of a switch. Has a switch operating system on it, some kind of API, a driver to talk to the chip. And if it's a relatively fixed function ASIC, that ASIC can use the TTP to say, this is how I process packets. So it allows it to express the way in which you can use it. I've deliberately drawn this arrow going from the bottom up because this is the design process. It's a data sheet from which you determine how you can use the chip, and then you design that system around it. But there are also programmable switches, as we know. These switches are more programmable than the fixed function ASICs, and it begs the question of, should we be doing something? Should we be allowing programmers to program in a vendor agnostic, a standardized, uniform way to program more flexible devices so that they get the benefits that you get from the vendor agnostic abstraction without having to have this bottoms-up approach? Okay? So we're well used to this in computer systems and CPUs. We program them, and then we run the program. NPUs, it's pretty much like that, depending on what the NPU is. In FPGAs, you describe the behavior you want, and then so long as it'll fit, then you're off and going. And there are more, as you've probably seen, more flexible match action ASICs that are just beginning to appear now. The Intel FlexPipe was obviously one of the first. Cisco has the Doppler chip that they use. There's XPliant, there's Barefoot, there's others that are doing similar types of activity. And you can think of these devices as top-down. These switches let us tell them how to process packets. So we tell them how to process packets. So just to belabor the point, the arrow goes the other way, which is the software, something from above is going to tell the switch, this is how the switch must process packets. So this is the core idea, the key idea of protocol-independent forwarding, is to enable this. So why don't we just call it top-down? Well, I'll tell you why we call it protocol-independent forwarding, because there are really three phases. They're obvious phases, but I want to call them out because I think they make it clear that the general approach. The first phase, phase 0, is initially the switch, whether it's a CPU, an NPU, whatever it happens to be, doesn't know what a protocol is. Just like the Intel processor sitting on this laptop doesn't know what a protocol is until I program it. It doesn't know how to process packets. So it is protocol independent. I need to tell it how to process packets. So we tell the switch how we want it to process packets. I'm going to refer to this process as configuration, because in some cases it's programming in the way that we're used to, and it could be in Java or C, something like that. But in other cases it might be something that's a little bit more specific to the task at hand. And then the second phase is, or phase 2, is the switch runs. I'm going to refer to this as the runtime. So basically, you configure a device or program it, and then you run it. So while these are distinct phases, they're not necessarily distinct in time. These could overlap in time. You could be reconfiguring, changing the configuration of a device, adding a new protocol header, adding a new statistics counter, something like that, while it's up and going. And that could be part of the way that it's configured, and that would be dependent on the device itself. So some devices, you can imagine, would do this better than others. But it helps to think of them as distinct phases only from the point of view of the function that's being performed. So when we started thinking about this in the P4 activity, Huawei had their activity going on in protocol oblivious forwarding. Sorry for all the names and the name confusion. And then there was the protocol independent forwarding activity that was also just beginning to get started. There were sort of really 3 common goals that seemed to be on everyone's mind. The first was protocol independence. Devices, allowing for devices that are that you can program to speak a number of different protocols or have a number of different functionalities. And it seems as though there's 2 main things that you need in order to make this happen. You need to be able to configure some kind of packet parser in the device. You need to tell it how it's going to process packets, in the sense that you need to start by telling it the headers that it's going to see on the wire. So these are the headers that you're going to see, or the headers that you're going to create. So the parsing is really a typing of the fields, or the typing of the header fields, as you would see on the wire. You next need to define a set of match and action tables, because that's what we do. That's how we process packets. And these are the match and action tables that are going to process these headers. The second goal was target independence. And that was the scheme that we came up with needed to work on a number of different targets, all of the ones I listed earlier, and hopefully more that don't yet exist. So the idea was to not only support a variety of different targets, but then also give an incentive to others to create new, more flexible targets in the future. So we need to be able to program without knowledge of the underlying switch details. Just like when you program in Java, you don't program in terms of the ARM or Intel instruction set. You just program in a way that is target independent. So we wanted to create that sense of target independence at the time that you're describing the behavior that you want. And then we'll rely on a compiler, just like we used to in software environments, to configure the target switch. So it doesn't have to be that the human has to get involved in the loop. As you can imagine, these devices, if they're a CPU or an NPU, are very, very complicated. And so it's beyond the capabilities of a human. And the third one is we'd like it to be reconfigurable in the field, in that you could change the behavior of the switch, maybe to simple things like change the size of tables, or add new protocol headers, or change the entire way in which it processes packets in the field so that you don't need to replace the device. So this means that you need a way to change the parsing and the processing once it's in the field. Okay, let's take a look at the abstract forwarding model. So here's a sort of a generic. The abstract forwarding model starts with, initially, a switch that's unprogrammed and does not know any protocols. The components of the abstract forwarding model are shown at the bottom here. They're roughly in sequence, although actually we make no particular assumption about their sequence, other than that there is a parser at the beginning. There may be more parsers, there might be more parsing steps, but that there is a parser at the beginning that is going to figure out what the headers are on the wire, extract them, and then pass them along to match and action tables. Those match and action tables could be in series, they could be in parallel, they could be a combination of the two. There's nothing in the sort of the abstract forwarding model that assumes one model or the other. And there is assumed to be some metadata that's present, that's available for processing, things like the port through which the packet arrived, the time at which it arrived, things like that that would be helpful during the processing. And then as it's a switch, it needs queues and it needs a mean to schedule packets into and out of those queues, decide which ones to drop, etc. So there is assumed to be some queues and scheduling. They may be at the egress, as is shown here. They may be in the middle. Again, the abstract forwarding model makes no assumption. Okay, so now that we've got this underlying abstract forwarding model, and that abstract forwarding model could be running on any of those devices I described earlier, that abstract forwarding model needs to be programmed. We need to tell it how to process the packets. So first of all, we need to author the protocols. So we need to tell it what to do. So I've shown the name of a program here, L2L3.P4. This is because of the P4 language that I'll be describing in a minute, but you could imagine other high-level languages that could be used for describing how packets are processed. So first of all, we describe it, or we go get, hopefully we go get somebody else's code that somebody else has painstakingly written to describe the behavior that they want. And then we compile it down to the device. In this particular case, I'm going to compile it down to this abstract forwarding model. And wow, PowerPoint's really fast at compiling. We've compiled that now. And we're going to configure the chip by telling the parser what to do. So here's a little parse graph, which could be turned into a state machine, for example, or whatever it is that's used on the device for parsing packets. And then we need to send something down to the match action tables, for example, to say, this is the sequence in which I want things to be processed, this is how big the tables are, this is the dependency that might exist between different processing stages, etc. So once we've configured the device, it's ready to run. And so now our switch OS and our runtime API can then add and delete entries, rules into those tables. Right? So this is the model, the sort of the programming model. You configure it, and you're configuring it by telling it how it's going to be processing packets and how it's going to be accepting rules. And then afterwards, you give it the rules during the runtime, just like we add and delete OpenFlow rule entries today in the OpenFlow model. It's very similar here, so we assume that's a runtime operation. Okay. The example I gave of L2, L3 doesn't look very ONF-ish, right? Doesn't look very OpenFlow-ish. And in fact, there's no particular reason why that program, that P4 program, is just limited to L2 and L3. One thing that you could do, which I hope that many of you will, is you could write a program called OF 1.3.P4. And in that case, you're telling the devices underneath to behave as a OpenFlow 1.3 compliant switch. So you could think of this as having two advantages. One is if you're operating in a network where you have devices that it benefited you to have OpenFlow 1.3 devices, then you can now have compatibility with those devices. Some of them more fixed functions, some of them programmable, allows you to do that. The second thing is that actually it can provide you with a way to specify OpenFlow 1.3. And sort of interested in this possibility way down the road as a way to unambiguously describe what we mean by OpenFlow 1.3, 1.4, 1.5. I'm not here to propose that today, but I think it's something to think about and bear in mind, because then you actually have an executable model that you can test against, and so you've got then an unambiguous specification. But the good thing to point out here is that with this approach, this approach then is complementary with the OpenFlow 1.x protocols that we have today. So it's designed to coexist and live alongside. So let me just go through, I'm going to whistle through some code examples using this P4 language, and then I'm going to say a little bit later that you shouldn't think of this as tied specifically to this P4 language. I would like it if we can entertain the idea of other high-level languages as well. Through a sort of a common structure. I'll explain that a little bit later, but bear with me, I'm going to go through some P4 code examples to start with, just to give you a sense of what's involved. So there are really four parts to a P4 program. First is we need to express the headers and fields that we're going to be using. Then we need the parser. The parser will figure out how to extract the headers from the wire and recognize the appropriate headers. Then we need the match action tables. And then we need some way to express and describe how packets will be processed by that set of tables. So in the headers and fields, I'll just give you an example. Here's an example of what an Ethernet header might look like, expressed within this P4 language. It should be pretty recognizable, a sort of a C-like language. We're declaring a structure here, a header type of Ethernet with the fields that we would expect, and then we have an instance of it that we can then use in the program so that we can talk in terms of the fields that we've extracted. Here would be another one for VLANs, and here would be one for metadata. So the P4 language assumes that there is some metadata available that any switch would make available for processing things like the port through which the packet arrived, the length of the packet, and so on. The next step is we need to parse the packet. So the parser is defined in P4 in the following way. So this would be the process of parsing an Ethernet packet. We need to extract the Ethernet header first, and then we might be switching based on a field, right? So we need to figure out what's next in the parse graph. This is equivalent to saying what the next state is in the parse graph. So in this particular example here, if we find that there's an ether type of type VLAN, then we move on to extract the VLAN. If we're parsing IPv4, then it might be that we move on to process UDP or TCP header, depending on the protocol field that we find. Probably no surprises here. There are a million ways that we could express this. This is just one example, but it's just to give you an idea of how such a high-level language might be written to describe how parsing would take place. The match and action tables specify which field to examine in each packet, the actions that may be applied. Now, the actual actions will be defined by the rules that get put into the tables, but it's helpful to give a hint in advance as to the actions that might be used by a table so that you know how to make sure that the data is available to that stage of the processing. And then, if you want, then indicate a table size, so that's supported within the language. No surprise, it's set up as a structure here. In this case, the match and action table for the VLAN. So first of all, you read, and that's the matching process. In this case, it's an exact match. You can see on the right-hand side on a couple of the ports. These are the set of actions that you might perform that a rule would be allowed to call upon, those actions being drop or extract the ingress logical interface. Similarly, for unicast RPF, it will be a different set of actions, a different set of match and a different set of actions. The matches here are assumed to be ternary rather than exact. Again, this is being expressed by the programmer as to whether the underlying hardware is able to do ternary matching. That's on how it does it and how it implements it is not a detail that we want the programmer to have to worry about. So if it gets implemented as a try underneath or as a TCAM, that's entirely up to the underlying device to figure out. The last thing we need is actions. And actually, actions is where all the action is for two reasons. One is it's the processing that takes place on the packets. The second thing is picking the action set is probably the hardest part of the whole process. In other words, figuring out what set of actions, what primitive instruction set is needed for a device or for the language. Make it too complicated, and it's too hard to build a high-performance device. Make it too simple, and you can't do useful stuff. So it's a balancing act to try and figure that out, and this is where I expect most of our work and activity will be over the coming months. So the basic idea within P4 is you express in terms of actions, and those actions are themselves build up a set of primitives. And those primitives may be natively supported on the hardware, or they may just be implemented on a CPU or whatever the device happens to be. But there is an assumed primitive instruction set from which more complex actions are built. And the assumption is that when you describe an action, you're describing it in terms of those primitives, and that all of those primitives are assumed by default to operate in parallel, unless you say otherwise. So it's just a collective, you can think of it as the macro, but in one in which all of these primitive operations will take place in parallel. So the primitives would be the things that you would need to modify a field, add or remove a header for encapsulation and decapsulation, clone for things like span, recirculate in order to be able to do more processing, and simple stateful operations, counters, meters, polices, things like that. So here's an example of an action being defined for extracting the logical interface. This one here is in terms of a number of modify actions. There's 6 here. They're all assumed to operate in parallel in order to implement that action. The last thing that we need is, now that we've got the parser to tell us what fields that are going to be extracted, we've got the description of the match in action, which tells us what to match upon and then the kinds of actions that we'll perform. We now need to say for each individual type of packet how we're going to process it, what the control flow is for individual packets as they pass through this device. And so this is the control flow. This example here is just a very simple one, just called ingress, for as a packet arrives, what are the things that we're going to do to it? So we're going to apply a series of tables. Those tables are then going to perform the actions depending on the rules that are found in those tables. And so I won't go through the example here. They're all the things that you would expect to see, a sequence of tables that you would expect to see in any device. I hope there are no surprises here, in the sense that you haven't seen anything that you wouldn't expect to see in a high-level language describing it's not particularly high level, but a higher than firmware or higher than Verilog, a language that's for describing how packets will be processed. What we've observed in thinking about this over the last few months is there are actually a surprisingly large number of use cases that one could imagine for such a language. So it could be used to describe switches, of course, routers, firewalls, gateways, load balancers, a variety of different things. And again, they may be possible to compile down to any target, or there may be some targets that you're able to and some that you're not. They are, broadly speaking, I would think of them as mostly stateless. They're not highly stateful operations. In other words, they're not applications like DPI where you're having to reconstruct TCP state or flow state in successive packets. Little bit of statefulness is okay for things like polices and meters and counters, but general high state, it's not really designed with that in mind. So the moniker that I carry around in my head is P4 is for plumbers. P4 is for those plumbing, redirecting packets, deciding which ones to forward, which ones to drop, how to process them in order to send them towards their destination. And I think that's a sort of a good working model to keep in mind. So before I go on and talk about the ONF activity, I just wanted to point out that there is a P4 website if you want to learn more about P4. P4 was, there was a website that got put up about a week or two ago. P4 stands for Programming Protocol Independent Packet Processes. It was originally, there was a paper that was published this summer written by the folks shown here. If you just go to p4.org, you'll see a spec of the language and a copy of that paper. And then over time, the idea is that we'll see some open source code contributed to that to allow for compiling down to a variety of different targets. If you want to contribute to p4.org, consider contributing to the language. Contribute a compiler to your target or somebody else's target. Contribute new tools. So the world will need P4 debuggers to help us write those P4 programs. Code coverage tools, a variety of different types of tools to help people in doing their development. So I would encourage you to consider doing that. So the P4 view of the world looks a little bit like this. It's just a redrawing of the figure I showed you earlier. There's a P4 program or library that you may have got from someone else that you then combine, put into a compiler, and then compile down to create a switch configuration. Hopefully, there will be compilers for different targets for P4, and a variety of them may appear over time. However, the problem with this model is it ties us, if we all were to jump onto this bandwagon and say, hey, let's all create P4 compilers and P4 programs for different targets, it would make it very hard for the P4 language itself to evolve or eventually be replaced. And while personally, I've spent a lot of time thinking about and working on P4 over the last year and a half. I don't pretend that it's the be-all and end-all and it's going to be the final word in languages for packet processing. Just like with everything that we do, I hope that one day it gets superseded by something better. And I think that's a model that we should all keep in mind. And that P4 itself will get replaced by something that may be higher level, it may be different in some other regard, and we should entertain that possibility, particularly as an organization like ONF. And I think that in the spirit of any good open source activity, we shouldn't lock ourselves into a particular approach. We should think very carefully about where the lock-in is taking place when we do this. So instead of this particular view, within ONF, we're going to take a slightly different approach, the way that you would normally expect to see happen with a compiled language, and that's we're going to go through an intermediate representation. So just like in the middle of GCC, you find an intermediate representation model to allow for different languages above and then different targets below. The idea is to do this here. So this intermediate representation shown in the middle, hopefully it's the smallest piece, not the largest piece as shown here. It'll be fairly simple, but this is the agreed upon new ONF open source project. So we took a proposal to the board yesterday and they were supportive of this. We're going to try and set this up over the coming weeks and months as a new open source effort. The idea here is that there would be multiple high-level languages. The box at the top just changed to say high-level language instead of P4. It could be a P4 program, a library. It could be something else. That's fine too. Then there would be a front-end compiler that was specific to the language that would compile from that language the intermediate representation. And then from the intermediate representation, there would be back-end compilers that were tied to particular targets. There might be one for OVS. There might be one for an FPGA. There might be one for a Huawei NPU. There would be ones for different devices. So over time, we'd expect there to be more back-end compilers that would be created, and I'd encourage you to think about doing that. So you could contribute to P4 and put the whole shebang in there, or you could contribute here and contribute a back-end compiler from that intermediate representation. So I think of this intermediate representation as a thin waist, right? Sort of the hourglass model that we're familiar with for the internet. This is sort of another example. If we as an organization can agree upon this intermediate representation, and there's a big if there, it's going to take some work to do that, then we can allow for a variety of different high-level languages, each with their own front-end compiler, and a variety of different targets in the back, each with their back-end compiler. So this then leads to a fourth goal beyond the three that I mentioned earlier. So in addition to protocol independence, target independence, and reconfigurability, it's language independence. And this is the approach that we're going to try and take within ONF to give us that choice. So now let's talk about this intermediate representation. It's all very well to show it as a red rectangle in PowerPoint, but what's actually inside there? Well, the goal is clearly to allow new languages above, compile to many devices below, uniquely define how packets are to be processed, keep it simple. All of those things are easily said, but a little bit harder to do. And the conclusion we've come to is it's really going to be about trying to agree upon a simple instruction set. And I'm calling it here a plumbing instruction set. So the proposal is that we focus to start with on agreeing upon a simple plumbing instruction set, which is the bare minimum that you need in order to process packets, steer them, drop them, etc. And then for those who are more concerned about using such a language to describe DPI, security, etc., let's create new instruction sets down the road once that initial work has been created as a superset of that plumbing instruction set. And then a device can declare, I will just do the plumbing instruction set, or I will do all of these instruction sets, or pick one, depending on the application that it's targeted for. So, okay, what are the components of the intermediate representation? It appears to be that there are three things that we need, right? So this is going out into a little bit of uncharted territory. It appears to be that we need three things. We need that plumbing instruction set. We need a way of describing the parsing, so a parse graph. And then we need some kind of representation of how the tables will process packets. So I tend to think of this as a table graph. If you're looking for an example of this, the P4 paper has a description of one of these table graphs, with each edge within this graph annotated with the actions that you would perform if you found a match in a table. So that's a way of uniquely, unambiguously describing how a device is to process packets. should try and keep this simple. We should try and keep it in a way that's human readable, but that could be easily generated from high-level languages. There's an optional piece of information which I list as a fourth piece here, that it's not entirely clear that this belongs in the intermediate representation, and that's annotating this table graph with dependencies that come from the control flow that would give hints to a back-end compiler so that it could exploit concurrency in the underlying device. One could argue that it's the job of the back-end compiler to figure out the dependencies, and so that it should look at the control flow and then figure that out for itself, or one could argue that it should be there for everybody to be able to exploit. I don't have a strong opinion one way or the other, and I suggest that we spend the next few weeks trying to figure that out. So in summary, there are really two steps to think of. One is the configuration process, high-level language, front-end compiler, intermediate representation, then from there through a back-end compiler to the underlying switch. At runtime, one could choose to use, underneath the control plane, the OpenFlow wire protocol. So you configure the switch to conform to one of the OpenFlow specs, and then use the OpenFlow wire protocol to communicate with the switch. So we think of this as going hand in hand. These are the two steps and the two stages that we need to think about. When it comes to contributing to the protocol independent forwarding open source project, as I said, it's approved by the ONF board. We're going to take this somewhat sort of drastic decision that not only will it be Apache 2.0 license, so anybody can use it, it will be open to all members and non-members. So anybody will be able to see it, anybody will be able to contribute to it, in the spirit of an Apache license and in the spirit of open source. So this will be an activity that will be visible to anybody. I'd encourage you to contribute code to an intermediate representation. It's open source, it's a technical meritocracy. It only works if people are actually contributing code. This isn't a working group. There won't be the normal deliberative spec writing process. We think of documentation as coming after the code rather than before the code. That's the idea here. Contribute a back-end compiler if you'd like to a particular device. My parting word would be to think about plumbing, to think of it as plumbing. I'm kind of curious to know what you think. This is pretty much summarizes what my teenagers thought when I told them about this. So if you like this idea, then figure out a way to contribute. You'll see this activity start up over the next 2 or 3 weeks. And let's see where it goes. By setting it up as an activity that's complementary to the OpenFlow wire protocol, if this fails, nothing changes. Everything will go along swimmingly just as before. If it succeeds, the only thing will change is we'll now have a compatible way to program these flexible devices. And so it should then live alongside the OpenFlow protocol after that. Thank you. I'm happy to take any questions.